Hey there, I'm Greta Shum, and let me ask you this. When you look at the ocean, what do you see happening? You might say, waves and a fish or two? Now let me ask you this. How are you doing today? You might say, fine. But life is way more complicated than that, and it's the same story in the Southern Ocean. You got gigantic wildlife, tiny wildlife, gigantic currents, storms, sea ice, and yes, waves. And just like most of us, the world's oceans are experiencing an enormous amount of stress. A lot of that stress comes from increased amounts of carbon dioxide. Wait, isn't carbon dioxide in the air? Let's take a look. As humans burn more coal, oil, and natural gas, they pump more carbon dioxide, or CO2, into the atmosphere. But the atmosphere and the ocean are in constant communication. An estimated 25% of the carbon dioxide from human activity released into the atmosphere ends up in the ocean. And carbon dioxide doesn't just sit around when it enters the ocean. It actually changes the chemistry of the water. Here's how it works. When carbon dioxide enters the water as dissolved CO2, it reacts with water molecules, H2O, to produce a weak acid called carbonic acid. Most of the acid immediately dissociates into hydrogen ions, H+, and bicarbonate ions, HCO3-. These new hydrogen ions are what reduces the pH, or increases acidity, and makes what we call ocean acidification. What's the big deal about some more hydrogen ions? Hydrogen ions are what make the water more acidic or more basic. But the acidity isn't necessarily harmful on its own. The problem is that those hydrogen ions bond with carbonate ions in the seawater, an important building block of life in the ocean. Dr. Jorge Sarmiento, professor of geosciences at Princeton University, explains.
It's funny that we call it acidification because in many ways the biggest effect of acidification is that you lose carbonate ion in the ocean, and so calcium carbonate becomes undersaturated, and organisms that make their shells out of calcium carbonate have a harder time living.
Calcium carbonate. It's the mortar that keeps our ocean biology intact at all. Let's hear what Dr. Ken Johnson of the Monterey Bay Aquarium Research Institute has to say.
So this little pteropods, they're a little marine snail. They make a shell out of calcium carbonate. The ocean is getting more acidic, and that dissolves calcium carbonate. So this little pteropod is going to have a harder time making its shell. In many areas of the ocean, it's really an important part of the ecosystem. Salmon, 40% of their diet are little pteropods, So they go away and the ecosystem changes.
Corals and other species are affected by disappearing carbonate ions, but pteropods are a fundamental marine food source. Plus, the oceanic food web is connected in more ways than we can know. Basically, status update, it's complicated. As the concentration of CO2 in seawater increases, the supply of carbonate drops and eventually crosses a threshold. And aragonite, the form of calcium carbonate commonly used in shells of marine animals and plants, spontaneously dissolves. You can see how this sea butterfly shell dissolves in acidic water, so that by the end of a month and a half, the shell, and consequently the organism living inside, are destroyed. It's a problem across the global ocean, but particularly in the cold waters of the Southern Ocean. Because, 1, cold water holds more CO2 than warm water, and 2, aragonite dissolves more readily in cold water. And 3, there's important vegetation in the Southern Ocean. Beyond all of this, there's already a lot of CO2 in this ocean because of all the organic matter that fell and decayed there. That's why the Southern Ocean will be one of the first places for acidification and undersaturation of aragonite to happen.
If the ocean gets too acidic, if the pteropods go away, which graze into plants, the whole thing changes, and I can't predict what's going to happen. I don't think anybody really can predict what happened. It'd be better to observe it and know.
Using robotic floats equipped with pH sensors to measure acidity in the seawater, the NSF-funded Southern Ocean Carbon and Climate Observations and Modeling Project, or SOCOM, is beginning to do just that. Observe and watch how this influx of carbon will affect chemical and biological properties of the Southern Ocean. We already know the Southern Ocean takes up 50% of the total amount of CO2 absorbed by the global ocean. If humans continue to burn fossil fuels at the current rate, the ocean will become too acidic for pteropods before the end of the century. Looking for more information about new research into the Southern Ocean? Check out socom.princeton.edu.